This is problem 120 from chapter 17. By pressing down with the finger at B, a thin ring having a mass m is given an initial velocity v0 and a backspin omega naught when the finger is released. If the coefficient of kinetic friction between the table and the ring is mu k, determine the distance the ring travels before the backspinning stops. So the ring initially is going this way with a velocity v0, and if it was rolling without slipping, your angular velocity would be this way, but your angular velocity is in the opposite direction because in this problem the ring is backspinning. So I'm going to draw a free body diagram first. I have the force of gravity acting downwards, the normal force acting upwards. I also have a force of friction. And if I look at what is happening here at point A, I have angular velocity going like this. So friction is going to oppose that, and you have a force of kinetic friction going to the right. The force of kinetic friction is going to cause the angular velocity to decrease, and the backspinning is going to stop when the angular velocity is equal to 0. So when the backspinning stops, that's when the angular velocity is equal to 0, and we want to find the distance traveled between when the ring is first set in motion and when the angular velocity is equal to 0. So we're going to look at Newton's second law in the x direction and in the y direction. In the y direction, the acceleration of the mass center is equal to 0. So I have the normal force is equal to m times g. I have kinetic friction in this problem, so I can go ahead and say the force of kinetic friction is the coefficient of kinetic friction times the normal force, and the normal force is m times g. So we have that, and then we can look at the sum of the forces in the x direction. The sum of the forces in the x direction is equal to mass times acceleration of mass center in the x direction. I have one force acting in the x direction, and let's go ahead and say that's the positive direction. So I have positive FKF. Then I have mass times acceleration of the mass center in the x direction. But if I say to the right is positive, that means my velocity here is in the negative direction. Okay, but I know what the force of kinetic friction is, so I can take this and put it in here, and that gives me mu k m g is equal to mass times acceleration in the x direction. The mass cancels out. Therefore, the x component of the acceleration of the mass center is mu k times g. And since I said to the right was positive, and this came out to be positive, that means this acceleration is to the right. So after looking at Newton's second law in the x direction and the y direction, I get to look at the sum of the moments, which is equal to the moment of inertia times the angular acceleration. So I have the sum of the moments about point G is equal to the moment of inertia about G times the angular acceleration. This is a thin ring. You can look up the moment in the back, the moment of inertia in the back of your textbook. Because all of the mass is at the same distance from the mass center, the moment of inertia for the thin ring is just mr squared. So that would be an easy one to calculate using the formula that we have here for the moment of inertia. Okay, so then if I look at the forces that I have here, there's only one force that gives me a non-zero moment. That's the force of kinetic friction, and that's going to cause rotation in this direction, which would be the positive direction. So I have the distance from the mass center to that force is the radius, r, times the force FKF, which, let's go ahead and say that's mu k mg, so it's r times mu k mg for the sum of the moments. That's equal to the moment of inertia times alpha. The moment of inertia is mr squared times alpha. I can cross out an m and an r, And if I do that, I get mu kg is equal to r times alpha. And I was asked to find the distance traveled before the back spinning stops. So I have here the angular acceleration, and I have here the acceleration of the ring. I need to find the distance traveled before the back spinning stops. I can use what I'm given here, which is the angular velocity when the back spinning stops is 0. And I know initially the angular velocity has a magnitude of omega naught. Now, we said here when we summed up the moments, this was the positive direction. So that means for the initial angular velocity, that's going in the negative direction. So my initial angular velocity is negative omega naught. My final angular velocity is 0. So I can say that change in angular velocity is final angular velocity minus initial angular velocity. So I have that, and I can solve this for my angular acceleration. And I have, that's mu kg over r. Mu k is a constant, r is not changing, so the angular acceleration is constant. I have a constant angular acceleration and a change in angular velocity. I want to find the distance traveled. To find the distance traveled, I can go back to my kinematic formulas, and I have equation 12.5. In order to use this formula, let's see, I know v naught, and I found the acceleration of the mass center in the x direction, but I don't know the time. The other choice would be to use this equation here, but I do not know the final velocity. So I can use what I have here to find the time when the back spinning stops, and then I can use equation 12.5 to find the distance. Because the ring is rolling and slipping, I cannot use equation 16.6 to find the distance traveled, or equation 16.7. I can't use that to find the distance traveled. I could find the change in angular position, but because it's slipping, I don't know how the change in angular position is related to the distance traveled. So I'm going to find delta t, and because this angular acceleration is constant, I can say by equation 16.2, my angular acceleration is equal to the change in angular velocity over the change in time. So the change in time is equal to the change in angular velocity divided by the angular acceleration. The change in angular velocity is omega naught, since this was initially in the negative direction. And then divide that by your angular acceleration. That's r times omega naught divided by mu kg. Okay, and initially if t naught is equal to 0, we can say the time when the back spinning stops is equal to r omega naught over mu kg. Then I can go back to equation 12.5, as long as I have constant acceleration. So if I go back and I look at the acceleration of the mass center in the x direction, mu k is a constant, g is a constant, so I have constant acceleration here. So I can use equation 12.5. Let's say s naught is equal to 0, so I have s, or we can say delta s for the distance traveled, is equal to v naught, but that's acting to the left, so that's minus v naught times, well, let's rewrite our equation first, delta t plus 1/2 times the acceleration of the mass center in the x direction times delta t squared. Now we can go ahead and plug things in. So delta t is r times omega naught divided by mu kg plus 1/2. My acceleration in the x direction is mu k times g times delta t squared, so that's r times omega naught over mu kg squared. So that is minus v naught r omega naught divided by mu kg plus 1/2 r omega naught squared, and then I can cancel this mu kg out with one of the mu kg's that I have in the denominator, which leaves me with mu kg in the denominator. And then, since both terms have an r omega naught over mu kg, let's pull that out over mu kg, and this is minus v naught plus 1/2. I pulled out one r omega naught, so I'm left with one r omega naught in the parentheses there. And this is delta S. Because we said to the right was positive and the ring is moving to the left, this should come out negative. Since it is moving to the left. And that concludes the solution for problem 120.